Alright, so I've posted 2 videos for today. The other video, please make sure you take a look at it. It has all the solutions and explanations to the assignment I gave you guys on Tuesday. This video we will be working on section 6.4. It deals with exponential growth and decay, some of which we've seen before, but others looking to set up a differential equation and use that. This allows us to see where that A equals P times e to the RT, that PERT formula, came from. Before I just said we're kind of skipping to it, but now we can see where this comes from. So we're going to be able to represent a quantity that increases or decreases proportionally to the amount present by solving a differential equation given initial conditions. In symbols, a quantity that is increasing or decreasing is changing at a certain rate. So we're going to write that as dy over dt, as some original amount is changing over time proportionally to the amount. So it's changing proportionally to the amount. So we're going to use k to represent some constant times this original amount y. Given an initial condition, so y at t equals 0 is going to equal some y sub 0 or y naught here. This is the initial amount. This whole equation here is our initial condition. And this equation is our differential equation. So what we're going to do once is just solve this differential equation for y in terms of t. And you're going to see that we're going to end up getting an equation that should look pretty familiar. All right, so I'm going to start with dy over dt is equal to ky. I'm going to use a separation of variables, so I'm going to have dy over y is equal to k dt. Keep in mind, k is a constant. I don't have an x value, and that's okay. I'm going to take the integral of each side. This is 1 over y dy, integral of k dt. Rather than x, I meant to say we don't have a variable t over here. So this becomes a natural log of the absolute value of y plus our first constant equals k times t plus our second constant. So then we get the natural log of the absolute value of y is equal to k t plus some constant here, using e as our base for each side. And again, I'm going to use that law of exponents to help us rewrite that right side. So we just get the absolute value of y is equal to e to the kt times e to the c. So then the absolute value of y, this part here, we could just say it's an a, is going to equal a times e to the kt. Now technically it's going to equal a positive or a negative. I am going to write that part as I explained in the homework problems. So y is going to equal positive a times e to the kt, or y equals the opposite of a times e to the kt. As I mentioned before in the homework problems, the initial condition will dictate what a is. So technically we could just say that y is equal to a times e to the kt. This should look familiar. We have seen in the past, just switching around some letters, that some amount is equal to an initial amount or the principal investment times e to the RT. So that's where this equation is coming from. But we could see it in many different forms. It could look like this. It could be the same as a is equal to, so some amount is equal to an initial amount times e to the kt. These pretty much mean the same thing. So it all depends on what variables you want to use. We're pretty much going to be looking at this. It could either even be y equals y sub 0, some initial amount, e to the kt. So these are all just variations of the same formula. So now that we have this, we don't have to go through all these steps again. We're going to start writing out the differential equation, and then we could just show that it turns into this when we solve that differential equation. So we're first going to take a look. Our first example is out of the book, page 338, number 2, sets up sort of a table for us. So if you do have your book, you could turn to it. So again, it's page 338. If not, I provided a picture of this page in one of my other posts. So let's take a look at that one. All right, so they give us some information at the top. So right away, they state that dy over dt is equal to ky. And there's 4 problems for this little part. And they give you either k and an initial condition, or they give you 2 initial conditions. So we're going to be looking at just number 2 for right now. Our next example isn't one out of the book, but it's going to be one to help you with a very similar problem. So what we're given here is that k is equal to a negative 0.5, and the initial condition y at t equals 0 is equal to 200. So we could show from this that we get this y equals a times e to the kt. We showed all of that on the last page. So we could say that this implies, or this leads to this. Again, the initial condition will lead to a specific sign that a is, so there's no need to keep the positive as well as the negative. We'll get the same result here. So we want to find the solution to this differential equation. So that's why we come up with this, but now we're just going to substitute in the initial condition here. So we're going to say 200 is equal to a. So we're given k, we're given our initial condition, which means we're after this a value right here. So it's going to be e to the negative 0.5, and then we have t is 0 when y is 200. So this whole part right here just becomes a 1. So a is 200. Therefore, y is equal to 200 e to the negative 0.5 t. Now, we really didn't have to show this, but it's good just to show the work and we understand what this initial condition means. But this means the initial condition is this a, the initial amount, which makes sense that it should just stay as the 200. So that's our answer for number 2. All right, our second example gives us an initial condition of y of 0 is equal to 20. This is different from the last problem. We have another condition that y of 4 is equal to 60, and we're asked to find k. Again, we're given that dy over dt is equal to ky, which leads us to a general solution here that y is equal to a times e to the kt. We're first going to use the initial condition because we still don't know what a is yet. So this initial condition will say 20 is equal to a times e to the k times 0. And again, this whole part just becomes 1. So a is equal to 20. And it allows us to set up an equation that y is equal to 20 e to the kt. Now we can use the other condition here of y of 4 is equal to 60. So we're going to say 60 is equal to 20 e to the k times 4, or 4k. Dividing both sides by 20, so we get 3 is equal to e to the 4k. Take the natural log of each side. So the natural log of 3 is equal to 4k, and k is equal, we're just going to leave it in exact form, natural log of 3 over 4. So technically we answered this, but just to write out a solution as well, y is equal to 20 times e to the natural log of 3 over 4t. So that would be our solution to this differential equation, but we, in this problem, it was only asking for what is the value of k. All right, this next example is going to be very similar to problems 5 through 8 on page 338. And say like numbers 5 through 8 on page 338. we're given here that we have an initial deposit of $2,000 and we have an interest rate at 6.5%. All right, most of the time when we go back to money that's compounded continuously for an investment, that's where we use the A is equal to P times E to the RT. Again, like I said, there's different versions of this. I'm, for right now, just going to be using this one. So question A is, how many years will it take to double your money? All right, well, right now we're putting in 2,000, so we want to know, and again, we always want to show what formula we're using. So if I were to double 2,000, that means my final amount after so much time is going to be 4,000 is equal to 2,000 e to my interest rate is 6.5%, so 0.065 times t, divide both sides by 2,000, so we're going to get 2 equals e to the 0.065 t. Take the natural log of each side. So the natural log of 2 is equal to 0.065 t. First, we're going to write this as an exact value, so t is exactly equal to the natural log of 2 over 0.065, which is approximately, go ahead and type this into your calculator, pause the video. You get 10.664 years. And for these problems right now, we're not worried about rounding with years. We can have this decimal, so it is perfectly fine to leave it like that. So it's going to take a little more than 10.5 years to double our money. For question B, how much money do we have in 30 years? Well, this is just a straightforward, it's simpler than what part A is. We're just going to use our formula here. So we'll figure out how much money in 30 years. So it's A is equal to 2,000 times e to the 0.065 t. So then A of 30 is equal to 2,000 times e to the 0.065 times 30. Go ahead and pause this to type this into your calculator. Again, we're talking money, so this makes sense just to round to the nearest hundred. And you should get 14,057 and 38 cents. All right, so again, those are like numbers 5 through 8 on this page. All right, then our next example is our last example. It's not a huge section that we're going to be talking about, but still very important. So this one is actually going to be number 4 off of page 338. All right, so again, they're giving us number 14. All right, so here they give us an equation that y is equal to, now they're using this symbol. Again, it's just the initial amount. And then it's e to the negative 0.005 t. And there's two parts to this. We want to first find the half-life, the element's half-life. So this is talking about polonium-210, the number of radioactive atoms remaining after T days in a sample of polonium-210 that starts with an initial amount of radioactive atoms given by this equation here. So we want to find the element's half-life. This means the time it takes for half of the number of atoms to decay. Now we don't know how much is there to begin with, so we could just pick arbitrary numbers here. So if we let the initial amount, say, be 6, then y is going to equal 3. So we could set this up as 3 is equal to 6 times e to the negative 0.005t. We could have used a 1 and a 1/2, and that's what this is going to simplify to, because as soon as I divide both sides by 6, we're going to get a 1/2 equals e to the negative 0.005t. Take the natural log of each side. So then we get the natural log of 1/2 is equal to negative 0.005t. So t is going to equal the natural log of 1/2 divided by negative 0.005. That's the exact answer. And then this turns out to approximately 138.629 days, and we could leave it just like that. But again, type this into your calculator to double check. I want to label this. Please email me, as I always mention to you guys, if you have any questions here. There's a part B as well. For part B, it says, your sample will not be useful to you after 95% of the radioactive nuclei present on the day the sample arrives have disintegrated. For about how many days after the sample arrives will you be able to use the polonium? So 95% is gone, which means 5% remains. So we don't want to use the 95% here, we want to use the 5%. So kind of like at this step right here, this is saying half of it's remaining, so we have 5% or 1/20th. So we could set this up as, again, I'm just going to go back to writing out the formula I'm using. So I could say that this is 1/20th. You could still leave it as 0.05, it's fine. E to the negative 0.005t. Take the natural log of each side. So the natural log of 1/20th is equal to negative 0.005t. So the exact answer here is t is equal to the natural log of 1/20th over negative 0.005, or approximately, pause again if you want to type it into your calculator, 599.146 days for 95% of this element to be gone, and afterwards will not be useful to us. Alright, so give this assignment a try. I'll show you on the next page. Still giving you more time, some additional problems here. Here's that number 12 again, so if you weren't quite sure how to set it up, give it some more time now. In addition, also do 1, 3, 5, 7, and 13. Some more AP practice problems on page 91, 1 through 3, no calculator. The next set, 29 to 31 on those pages, 78, 79, and 85. Some of these, keep in mind, are problems that I've given you before, so you may recognize them, but that's okay. We still just want to go back and practice it, because maybe the first time around it wasn't too clear, but the more types of problems we go over, you go back to revisit these, they may become a little bit easier. Also continue with AP page 11, that number 6. Again, being a free response question here, allow yourself 15 minutes each time, even if you want to go back and retry the problem in its entirety as well. So I'll have this posted tomorrow. I may not show the answers tomorrow, still give you guys over the weekend, but I'll probably have notes up to section 6.5 tomorrow. Alright guys, hope all is going well.